So I'll just take this opportunity to welcome everyone to today's day two workshop. Most of you were here last week for day one. I hope you did enjoy that or benefited from it. As we saw, I think a lot of people have previously just used Excel, so this is a bit of a different experience. And like we always say, we're learning together. So today, Islam couldn't finish her presentation last week. So she's kindly agreed to come back and just finish that off today. So for those that were asking last week, she'll be looking again at understanding the applier for data manipulation, and then R in action, right? And then there'll be some group work, and then after the group session, we'll then have a recap in the main room, and then Q&As. Then we'll just have a mini break or a comfort break. Then Josh is going to talk to conceptualizing and choosing models. And then Karina will get into Markov modeling in HTA. Then there's going to be some group work, like the same recap afterwards in the main room. And then Hannibal will then join us later to talk to interpreting cost effectiveness results. And then there'll also be a breakout session then, and then at the end of the program, I will then close it off again. But I will be in the background and assisting with things.
Cool.
So,
hi everybody. My name's Josh. I think most of you met me on last week's workshop, and this is just a brief presentation on choosing the economic modeling structure for your HTA decision problem. We won't go through any R specific examples here, but I think it just plays into the whole idea that the right model is based on the decision context, should not be limited by your statistical software, and should be fit for the decision problem and the clinical pathways or clinical reality of the patient group you're trying to model. So the overall objectives of this presentation is to understand the role of economic models in HTA. Then we'll briefly discuss different modeling frameworks and how they align with different decision problems, and also briefly explore the strengths, limitations, and the appropriateness of these models for different contexts. So, as we discussed last week, HTA is a very broad, multidisciplinary process that is not only health economic related, but involves clinical experts, as well as considers the wider societal impacts of health technologies. And health economics is one of the tools that are used during this process. But more specifically, HTA economic models are used to help synthesize data from the available sources you may have, and then we estimate the long-term outcomes of clinical trials or registry data, etc., and their costs and benefits and how they impact patients over time. So, why model choice matters? Well, the structure of your model has a strong influence on how it accurately reflects disease progression. It's also about the transparency of the model and the credibility, and therefore the credibility of your analysis. So this is a very important point when engaging with stakeholders or decision makers. Often being able to communicate how your model works actually plays a very large role and is often more important than going for the most complex type of model. And then the model really also helps how types of uncertainty can be assessed or mitigated. So based on that, choosing the wrong model can often lead to biased cost effectiveness estimates. And this is a big problem if you're actually trying to show the true cost effectiveness of a product. You know, if as health economists, or if you're interested in this field, if you develop a biased cost effectiveness model, that doesn't accurately reflect an innovative product, for example, it can often lead to negative or non-recommendations from HTA decision makers. And choosing the wrong model can also mean that it may be over complex, or in the other extreme, oversimplified for the given decision problem. And then again, this leads to the fact that you're not accurately reflecting clinical pathways and patient outcomes. And then it can also lastly misalign with what the decision maker needs. So, in a context where HTA is only at its beginning, where they're evaluating drugs that have gone through multiple HTAs across the world, you may only need a very simple decision model, just because the cost effectiveness of that drug has been evaluated multiple times, and it has been determined that it's highly cost effective, for example. Whereas on the other extreme, if you are working on a highly novel gene therapy within the UK, for example, you might need a more complex model to accurately reflect the value of the product and how it might reduce chronic complications over time, for example, and therefore lead to cost savings. So a gene therapy, for example, might be a very expensive once-off costs, but those costs, you have to think about how those costs are offset in the long term by the fact that patients no longer need chronic standard of care. So overall, what should drive your choice? So the first place to start is always your decision problem. So what type of technology is it? Is it for reimbursement of a new drug? Is it a diagnostic tool? And then I think probably the most important part is actually considering the clinical pathways or the clinical reality of the disease. So it's natural history, how it functions. And I think before you even have an idea of the data that you may have or what your decision context is, understanding how the disease works and how best to reflect that in the model is probably the most important thing in my experience. So things to ask yourself is, does the problem involve time dependence or recurrence of disease outcomes? So for example, is there a time dependence on developing a certain chronic complication? Or is there a time dependence in terms of, as time progresses, is there an increasing risk for developing the complication? And it's important to think about what trade-offs you make in terms of the complexity versus how you can communicate how you've modeled that or structured that. Another issue is heterogeneity among patients. So are there very specific subpopulations that you may want to look at? How do you deal with that? Is there too much heterogeneity to form an average cohort value, for example? Or is it just simply a difference between type 1 and type 2 of the disease, for example? So when it's simply just, there's very clearly defined type 1 and type 2, just as an arbitrary example, then you can just run two different cohort models, for example. But if there's extreme variance between patient outcomes, then one could consider stuff like microsimulation. So you build your model all the way down to the individual level. But the issue with that, especially, for example, in the UK, is that, and across the world really, is that you often don't have sufficient data to actually run microsimulation models. And if you're on the consulting side of things, then companies also want to get their product to market, and there's all these other considerations that you have to take into account when thinking about your timelines, etc. And then also interactions between individuals, so how you account for synergy between complications. So for example, diabetes and heart disease, are you going to include a regression model in the background to model that interaction? How would you model it if you're using a cohort model? All of that. And lastly, if there's queuing, so for example, if patients are waiting at a screening center, for example? Are you going to use a simulation type, a more individual simulation type model, or can you use a cohort model for that? And again, it's really important to consider how much data is available after you've looked at the clinical reality, what is feasible, and would a microsimulation model, for example, actually be better than a Markov model if you have very limited data? And the answer often is no, because if you try to run a microsimulation model with a whole lot of assumed values, there's often far more uncertainty in that model than there is, for example, an average outcome model or a state-based transition model like a Markov model. And that basically leads to what level of complexity is justifiable. And that's also a very important point to think about when you are thinking about what type of model to choose for your decision problem. So here's a table of the very common frameworks used for health economic modeling, from most simple to most complex. So we have the decision tree, which I think most of us might probably familiar with, and Bouclet also made a presentation on a decision tree last week. So the strengths of a decision tree is they're really simple, they're fast, they're really easy to communicate to decision makers. So if you are in a context where HTA is a really new process in your country, and you need to communicate this to the medical board or something like that, this is often a really great way to do that. The problem with this is that they are very limited in what they can do. And if the disease is quite complex with a lot of outcomes, it often actually becomes quite overly complex in terms of how you have all your branches and all your outcomes, and it can actually become almost very hard to interpret and read and keep track of. So then we also have our Markov model, which Karina will present following my presentation, and she'll discuss a basic Markov model with you, how do you adapt it and how to use it for future R coding models that you want to do. And Markov models really are the very common and reliable model of choice within HTA, especially across Europe and other nations such as Canada or Australia. And it's because these models, even though they can't track patients over time, they are pretty flexible, and they are an easy way of representing patient outcomes and pathways over time. And there's different techniques that you can overcome this memoryless assumption. But again, one is limited to the type of software that you're using. So it's much harder to implement stuff like several tunnel states, or to change your Markov model into a more complex continuous time model, which I can discuss if you guys want me to at the end. And in R, that's so much more easier than Excel. And in fact, in Excel, to create a continuous time model rather than a discrete time Markov model is almost impossible. And then following on that, from that, we have our more individualized patient models. So you have microsimulation, which tracks individual histories over time. It's very computationally intensive because instead of simulating a entire cohort over time, you basically simulate one patient at a time. So every simulation that you run, it's just tracking one patient's outcomes over their lifetime, and then you might run it again with slightly different characteristics and inputs, and then it stores the history of the second patient and so on. And from there, you get a better picture of patient outcomes, etc. And then discrete event simulation. This is quite a new thing, and it's similar to microsimulation, but it uses events as basically your health states. So people queue, and then they might move to screening, and etc. This model in particular is not widely applied in HTA, and in fact, often decision makers, as well as your external assessment groups, which critique the HTA submission models, they often have a hard time accepting or interpreting these models because they are very data hungry and they are very programming intensive, and they can be extremely complex. So you'll see these sometimes submitted, but very rarely are they actually well received by the HTA body. And then lastly is your more epidemiological models, such as a dynamic transition model or dynamic model. And this often is for infectious disease with transmission. So ideally, you want to do these types of models for any infectious disease or communicable diseases. But again, you can also do that using microsimulation. So often within health economics, when this happens, you often see microsimulation more for that. But the great thing about a dynamic model is that you can incorporate parameters that capture herd immunity or herd effects of the disease. But again, these are very data hungry and can become very complex and often require statisticians to be involved.
So Josh, sorry, while you're still there, there was a question from Jackie.
Yeah.
In the chat, if you want to look at it, or do you want me to read it out?
Could you read it out?
Okay, it says, could you share a bit more about continuous time versus discrete time models? And then why would continuous time model be difficult to implement in R? Yeah.
Okay, so I'll answer the first part quickly. Continuous time is not hard to, it's hard in terms of the statistics and the programming involved, but it's not hard to implement in R. It's very hard to implement in Excel or other spreadsheet-based software. And then, Butler, if you could just remind me to answer the discrete versus continuous time mark-off at the end.
Okay, cool.
So this is just some decision problem examples with why you'd choose different modeling frameworks. So for example, asthma treatment, it's a chronic condition with quite regular flare-ups. And here you can use a Markov model with health states. For example, with the flare-ups, you can use mild, moderate, severe, and death. And that is just an easy tracking of a chronic condition. So again, just reflecting the fact that a Markov model is really great for these chronic conditions that change over time, where patients move to different categories over time, depending on their disease activity or severity. So a new surgical device, so for example, a new diagnostic device or something like that. Here, a decision tree really shines, and it's much better to just have a yes/no simple outcome type decision tree for something like this. And again, what you'll often see in HTAs in the UK, for example, is that if there's a new surgical device, or even if it's a surgery intervention, what will happen is you'll first have your decision tree that will have either your responder or non-responder, and then you'll feed those outcomes into your Markov model. And that's something we'll probably touch on at a later workshop, but this is also something you can think about. So if we are to simplify a Markov model, a great way to do that is to first use a decision tree with very set outcomes that happen over a week or two, and then you feed that into your Markov model to basically model the long-term outcomes of these patients. So the third example is cancer immunotherapy. So because they're time to event outcomes such as progression-free survival or overall survival, there's a lot of variation in patient risk, and therefore you want to consider this variation in outcomes between patients. And here you can use a microsimulation model. Something you see far more often is a partition survival model, or PSM. And this just directly takes your survival models and takes the difference between, for example, your overall survival and progression-free survival and considers those as almost implicit health states. But you can also, for example, if there's very limited, if there's immature survival data, for example, it's actually a good idea to use a Markov model so that you have an explicit, for example, progression-free survival health state and then an overall survival health state. And you can actually just make your overall survival a Markov transition between health states. And that really helps with reducing uncertainty in immature OS data. And then finally, COVID-19, something we are all familiar with. So because it's an infectious disease, ideally you would want a transition, dynamic transition model. And this is something that requires often a whole team to do. So during COVID, for example, I know of someone who joined the UK Health Security Council, and together with epidemiologists and statisticians, they developed a COVID-19 dynamic transition model. But again, this isn't something we often see in HTA, just because a COVID vaccination strategy often is something that's implemented very widely by governments, and it's not necessarily a specific targeted intervention for a target population. So just recapping on the brief idea of what's the strengths and weaknesses of all these different models. So again, a decision tree is really transparent and intuitive, but it can lead to, if it's a complex disease, it can actually quickly become overly complex, and it's also it's not able to actually model recurrence of disease, and it doesn't consider time at all in its model structure. And then a Markov model, so really good for modeling long-term repeated events, assumes the transitions between states are only dependent on the current and previous state. Again, there are strategies to overcome this, but again, that is also really dependent on your modeling software. So for example, in Excel, you can implement certain strategies, but it can quickly become, those techniques can quickly overburden an Excel model, and it can sometimes take a day or two, for example, to run just a probabilistic sensitivity analysis. And then microsimulation. So this is really good if you have very clear patient level variation, and there's a lot of randomness between patients. But because of that, it also requires a lot of data and computing power. And then following on to that is discrete event simulation, or DES. So it's really good at modeling queues and resource use, but it's much harder to validate and explain. And again, it's very hard to program and also requires quite a lot of data. And finally, dynamic models, really good at communicable diseases and indirect effects, but they are completely impractical without enough or sufficient amount of data, and can also become quite hard to explain. So based on my experience within the UK, I think I'm just going to provide some practical advice. So it's always great to start simple and then only add complexity when it's justified by the decision problem or available data. And my most important thing for me is to be realistic about the clinical pathways. And this comes before all else. So before looking at the data or anything else, always think about the disease and whether you are best reflecting disease outcomes and pathways. And then it's really important to also consider who you are engaging with. So are you engaging with stakeholders and decision makers who are familiar with models, or is this a group of decision makers and stakeholders that are really unfamiliar about these types of things? And is it best to communicate a very transparent and clear model, or can you actually make quite a complex model and do these decision makers want something as accurate as possible, for example, when they want to think about implementing COVID vaccination strategies? And then another really good practice is to consult clinicians and sometimes an external health economics expert as well, just so that they can pick up on any gaps that you might have missed. And a clinician is also really good at, or a group of clinicians are also really good at validating your assumptions and considering whether your model reflects the overall disease process and even captures the most important aspects of the disease. So another point here is that, when you're thinking about a disease, what's important is to capture the elements that your technology makes a difference on. So, for example, if the standard of care and a new technology, if the new technology doesn't reduce heart disease, there's not that much point in capturing it, just because the patients will likely have similar outcomes and therefore similar costs and utilities. And therefore, but if, for example, they might stop something like diabetes, then it is really important to capture that difference. So also be flexible. So if you're really unsure about what's the best decision model to choose, it's also a good practice to think about developing 2 different conceptual models. And even if it's, for example, 2 different Markov models, just with different structures, that's also a really good practice to present to clinicians once you're going through review.
Josh, sorry, so if you can wrap up in the next 4 minutes, please.
Yeah,
Thanks.
Perfect. So I'm going to run through this quickly. So again, some common pitfalls to consider when you're doing your models: using complex models without sufficient data or justification. And this leads to the fact that people who love modeling or might really get into it, it's really bad to focus on the maths rather than the clinical reality. The maths doesn't matter when it comes to actually reflecting what happens to the patients over time. Also ignoring structural uncertainty, so not accounting to that. For example, not developing adequate scenario analysis or deterministic or probabilistic sensitivity analysis. It's also really good to always document all of your assumptions or reasons for implementing the structure you did. And then another pitfall is selecting a model just based on your own preference rather than whether it's fit for purpose or not. So key takeaways: model choice is driven by the decision context, disease characteristics, and the available data. Simple is often better. Complexity does not mean it's more accurate. In fact, it can be the opposite often, especially when you don't have much data. And always use the model that best reflects the real-world clinical reality and pathways without overfitting to those pathways. So thank you. I'm going to open it up for questions.
Okay. So I don't know if you want to go back to the chat. I mean, there was that question from Jackie about sharing a bit more regarding continuous time versus discrete time models.
So discrete time models, it's really hard to explain. So I hope I gave you some idea. But a discrete Markov model uses clear cycle points, so cycle 1, 2, 3, and that cycle might occur every month or every year, for example, or even every 6 months. And it's basically deterministic cycle points. In a continuous time Markov model, what happens is you basically behind the model trace, you have a time to event model, which estimates the time that it takes for a patient to move from state 1 to state 2. And so you basically sample a cycle time for every cycle. So one cycle might be a couple of days, another cycle might be 8 months, and it all depends on the model that is calculating how much time an individual patient might take to transition to the next cycle. So basically, the transitions occur at random times depending on the risk and the model that's doing that, whereas a discrete Markov model does that at set times, so every month or every 2 months, depending on your choice that you make. Hope that makes sense.
Okay, thanks, Josh. Thanks, appreciate it. So we will now hand over to Karina, who will be talking to Markov modeling in HTA. Since you were not with us in day 1, Karina, if you can just maybe please briefly introduce yourself. Yeah. Thank you.
Yes, sure. Thank you so much, Boosle, and thank you, Josh, for giving us a good overview of lots of models that are available and when to choose what.
Thanks, Green.
Thanks. Yeah, so firstly, my name is Carina Ber. I am a health economist at Humanity, working basically as a kind of consultant for multiple pharmaceutical companies and yeah, working with HTA submissions all across the world and sometimes global HTA or global cost-effectiveness models as well. Yeah, and I have a background in industrial engineering, and I did a PhD in health economics at the University of Twente in the Netherlands. And I'm from South Africa, which brought me to the low and middle income country workshop and the consortium. So very happy to be here and happy to walk through this model with you. So please feel free to ask questions at any point. You can just unmute yourself and go ahead and ask it as we go. So today we're looking at a Markov model example. So firstly, I have some learning goals for us. So first we want to understand a little bit about the theory. Yes.
I don't know if anyone else is having the problem, but I can't see your screen, but it might just be me. So if anyone
I can see her screen. Yeah, I can see.
Okay, so it's probably me then.
Yeah.
Okay, thank you.
Okay. Great. Thanks for flagging anyway, Josh. So we will do a brief look at Markov models and the theory behind it. I won't go into too much detail given our time limitations today. And I will give you an overview of the setup of the DARTH cohort model in R. So DARTH is a working group, and they developed quite a few different templates that they've also published, and it's available freely, so you can use it and adjust it according to what your needs. So then I'll give you an overview, and we'll also walk a little bit through adapting the DARTH cohort model. And yeah, we're assuming some pre-knowledge in terms of just basic health economics and utilities, qualities, ICERs, and those things. So if we go through the Markov model, firstly, what is a Markov model? So it's a cohort state transition model. So basically you have a hypothetical cohort transitioning through health states. So you predefine your health states, and this cohort moves through the different health states. And in the end, you have a group result presented by a single number or a single ICER. And what's really important is that a Markov model is memoryless. It's called the Markovian assumption. So basically it means that the health state that the group is in does not depend on previous health states that they were in. The health states are mutually exclusive and collectively exhaustive, meaning that a proportion, each proportion of the cohort can only be in one health state at a time. And they always need to be in a health state, so they can't be in no health state. And we assume that the cohort is homogeneous within each health state, so we're not looking at individual level dependencies or differences. So if we look at the basic Six Sigma model, we have 4 health states. Patients can move from healthy to sick, for example, from sick to sicker, from sicker to death. Actually, from every way, patients can die. In every state, you can stay in the state, and a person can also move from sick to healthy. So have cure. The cohort in this example is very young, so we have a 25-year-old group, and the time horizon is up to a maximum age of 100 years, so 75 years time horizon, and we have a cycle length of 1 year. Then we can look at a transition probability matrix. So in this example, yeah, very simple example, I think. But you can move from healthy and staying healthy, and you have more or less 72% chance of staying there. Yeah, all the values are given here, and what's important is that every row sums up to 1. In a cohort state transition model. So basically, just to illustrate what we're doing, so we have all patients can, for example, start in state A, and then you have a probability of moving or staying in state A, moving to state B, state C, state D, and this is this happens in cycle number 1, and then you move through all to the next cycle, and so forth. And every time you multiply the number of patients in state A, for example, by the transition probability of staying in state A, which then gives you the new number of patients in state A in the next cycle. And okay, you can also plot an ISA based on these results. I think for today I will not go into that. So if we go to the Darth cohort model, so basically I am going to walk through a few steps that I think is very important for us, and then I'll share with you the link to download the code, and you can do the exercises in group work at the end. So yeah, we're looking at the Darth discrete time cohort state transition model. So as Josh just explained, in this case, you have discrete time points. So our example is 1 year discrete time points. It's called a Markov model. We will look at the time independent model. So you can also look at time dependent, where your transitions between, or your transition probabilities depend on which time stamp you're in. But this one is time independent, so we're keeping it simple for today. And yeah, there are multiple different repositories from the Darth workgroup that you can download and try, and there's a tutorial explaining everything, so it's very useful. So for example, there's a microsimulation tutorial as well, and the cohort modeling tutorial, and there are also different packages that they use, for example, DAMPAC. So if we look at some basics in terms of the coding that's being used by Darth, it's important to know this to understand or be able to read the code. So basically all variables are divided into 3 parts. So the first part explains the data type that we're working with. So sometimes there is no first part, which means it's a scalar. There can be a vector, so just basically one short list of things. You can have a matrix, so quite often a 2D matrix with columns and rows. You can have an array, and you can have a data frame. These are often 2-dimensional, can also be 3-dimensional. Then we have a variable type, so we have a P for probability, we have rates, we have hazard ratios. In this example, we don't have a log odds ratio, if I remember correctly, but they also have this predefined, and costs and utilities to indicate what type of variable we're talking about. And then always a description to indicate, for example, if we have a cost, what is the cost for. So to give you a few examples, here we have, we'll just jump to the next slide. So we have the cost of being in a healthy state. So in this case, we have the healthy, sick, sicker, and death health states. So we have the cost of being in a healthy state. We have the rate of moving from healthy to death, which is basically the baseline mortality rate. We have the utility of being in the sicker state. We have the probability of moving from healthy to sick, and we have a vector containing the initial health states, or the initial proportion of individuals in each health state. So I made a few screenshots of the code just to make it easy to run through, but we will go into R a bit later. But I just wanted to show you a little bit of an overview, and it's easy to look at it just as separate chunks, especially if you are maybe still a beginner, instead of looking at the whole piece of code at once. So in the beginning, you have the general setup. So you predefine some of your important variables. So for example, the cycle length, in this case, 1 year, the age, as we discussed, the starting age is 25 years, maximum age 100, based on which you can calculate the number of cycles. Here we have the vector with the names of the health states. So as I mentioned, we also have here, for example, the discount rate of the effects and the discount rates of the costs. And we also have a list or a vector with the names of the different strategies, and some other input parameters that we'll also use later. So if we look at the probabilities, you can calculate, for example, the probability of moving from healthy to death based on a rate moving from healthy to death. So you are transforming the rates into probabilities using this formula, which I hope you are also familiar with. And I think one thing that's important of this part of code comes to what we discussed, or what was discussed in the chat earlier, is that you can also sometimes do things a bit simpler by, instead of using the same code multiple times, or very similar code multiple times with the same formula, you can also use a function. So what I want to show here is that these 3 rows of code is the exact same, or does the exact same as these 3 rows of code. And here we have a predefined function called rate to probability with 2 inputs, the rate and the time step, which is the cycle length. And I think this is important, maybe especially for beginners, so to identify what functions look like. So sometimes it's difficult to know what was, if you're using someone else's code, which functions they defined and which functions are part of R. But in this case, there's in another script, there is a function that is predefined called rate to probability, and here you define it as a function, and there are 2 input values needed, a rate and a timestamp, and here it shows that t equals 1, so if the user doesn't provide a new t, then the time would just be 1. And within this function, we use the formula, which is the same formula that was used here originally. So 1 minus the exponential of negative rate times time, which is what we have here. And yeah, so basically the use of this is that this function can be used multiple times, and you don't have to, in this case, it's a relatively simple formula, but it is useful because you don't have to remember the formula every time and code it every time. You can just provide your predefined function with a rate and a time, and it will apply the formula and convert the rate into probability. Then if we look at other important parts of the DARTH code for cohort state transition model, one of the driving variables is called M or MT, and this is basically the distribution of the cohort across all states. And as you can see, there are different T's, so at different time points, there will be a different distribution. So I have a little screenshot with an example to make it easier. So basically, we have the 4 health states. And at the beginning of the model, we define that all patients are in the healthy state. And after cycle 1, this is the distribution. After cycle 2, this is the distribution, etc. And this is a very important matrix in the model, because it basically drives all your results, or you calculate all your results based on this matrix. Another important variable is called P in this model, and it's the transition probability matrix. So again, I have an example. So it's the probability of moving from one health state to the other. And yeah, for example, here you can see you can't move from dead to healthy. You can only stay in dead. So it's the last, or the last state. But you can move from healthy, staying healthy. You can move from healthy to sick and to dead, for example. So these are the 2 main driving variables, I would call them, for the model. Then if you're looking to run the model, you can search through the code to find it easily. It's just to run Markov model. And basically, this is a for loop which runs iteratively through every time point, every discrete time point. And for every strategy, so standard of care, strategy A, B, or AB, at every time point, the matrix M is calculated. So this is it calculates how many patients, or the proportion of patients in each health state. And then this, because it is a predefined code, it also includes lovely plots, which is very nice. It helps you to look at the model results and see whether it is realistic or what you expected. Then I think it's useful to just mention that in the code they used within cycle correction, using Simpson's 1/3 rule and discounting, as I showed you previously, there's a discount rate which can be separately defined for but hopefully you can still hear me. Please just shout if you cannot. Then lastly, or later in the model, they calculate the outcomes. So this is also code that you don't necessarily have to adjust, but it's good to be aware of where things are happening. So there's a loop through the number of strategies, so through every strategy, a vector calculating the utilities over all the different strategies is calculated, and also for the costs, same thing. And and then the sum over all time points is calculated for all the states, for qualies and for costs, which then gives you your total costs and qualies. But it is also useful, as you saw everywhere, there is comments with an explanation of what is being done. So if you're unsure, it really helps to read that. Then in total, the ICEs are calculated, and this data frame with a cost effectiveness analysis gives a very nice overview of the results. And again, some nice plots, so you can see the isoplane with the different strategies, showing the costs and the effects. So I have a few questions for us. I would first like to just in the chat provide you with a link. Sorry, it is this one. I think I closed it. I would just like to provide you with a link to the Darth GitHub repository, and you can download the code directly from there. So there's the link. And I have a couple of questions for you to answer. So open the code. If you need some help with that, just give us a shout. And yeah, the first 3 questions are mostly to see if you understand the code. So you can run the code to make it easier to read which values are in a variable, but you can also just get the answer from the code itself. And yeah, question 6, there is something that you need to adjust. Question 7 is a bit more advanced, so I think you probably won't have time to answer this question today, but I think if you have time, do start trying, and we will provide the codes on our GitHub afterwards to show you how to add an additional state. But let's quickly run through questions. So first one, just what is the annual probability of becoming sick while in the healthy state? So what is the probability of moving from sick to healthy? And also, again, probability of entering the sicker health state while in the sick state under therapy B. So if you go through the code, you will also see that every strategy includes a different therapy or has a, for example, a hazard ratio attached to it. So try to see if you can, if you can find that in the code, or if you can't find it in the code, if you run the code, you have the, I can also show you that. If you run the code, you can also see some of the variables saved already in your environment. And if you open them up, you can see the values in the variables. So these are, for example, the results, and you can read it directly from there. Going back to the questions, so then which matrices were used to obtain the entire cohort distribution between the different states through the whole analysis? So yeah, just which matrices were important, and maybe just provide a definition in your own words on what they represent. And then again, from the variables after you run the model, how many patients out of 100 were in the healthy state at the last cycle, so in year 75 of follow-up, and the same question for strategy A. Then what were the total discounted costs and qualities for strategy B? Again, try to see where you can find these things. So the important thing about these questions is to understand which variables you need to look at and what each variable represents. And then try to see if you can change the currency of the isoplot. So this is a bit of an adaptation of the code. The isoplot is in rows 337 of the code. Try to change it to your local currency. It's maybe a bit tricky, but we'll look at this together afterwards. And then, as I mentioned, if you have time left, try to add an additional health state, as yeah, that's quite a fun adaptation to do. So I think, Boucle, if you can help me, then we can divide everyone into breakout rooms, and I really want to encourage you to try to do it together. Try to switch on your cameras if you can, perhaps share someone's screen so you can talk through it together and walk through it together and try to make the adjustments. I can also just perhaps provide a screenshot of the slide in the chat, then everyone can refer back to it in the breakout rooms.
Okay. Hi, Karina. I was in group 2, and I think we had questions Bernardo, do you want to ask a question to Karina? Bernardo and Sayem.
Sure.
Yeah.
We were looking for the underlying data to actually run the code, because most of the questions, they imply that we have to calculate the probability or the number of patients, but in the functions, there are no probability
sorry.
matrices or stuff.
Yeah, so I failed to mention that on our GitHub page in the resources folder, like on our R-HTA and low and middle income country page, in the resources folder, there's a preparation document. I can copy the link and also just put it in the chat for now. And there you can find the steps if you don't know how to download the code from GitHub, but also towards the end of this document, it says to open the code from the analysis folder. So I can share my screen and just show you. So if you have
and then also
the code downloaded,
just to jump in, Karina.
Yeah.
Also open once you've downloaded that file, in order for the working directories to work and be self-contained, just open the project file, so the .proj. So once you've downloaded that, make sure you click on the cohort something .proj, R-proj file.
Yeah, and you can open it by right-clicking and then saying open with. Well, now it doesn't pop up for me. They open with RStudio. You can also open it from RStudio if you know how to do that, but that's how I always do it. And then in here, you can go to the analysis folder, and this is the script with the model in it. So the main part of the model.
Okay.
Yeah, I think we find it now. Yeah, thank you for that. And yeah, we were mostly inside the folder R. That's why we only saw the functions and other things.
Yeah, that's the more complicated stuff. But that's how you could also, to play around with that code, you want to use the stuff that's in the R folder to make the model more complex. So the analysis part is mainly your main settings, etc. And then the R folder contains your core modeling engine.
Yeah. So for now, you can stay in the script, run the code, make sure that you have all the packages installed, and there will be warning messages in the beginning, but as long as there are no errors, you can answer all the questions. Yeah, so the error in the chat here says that the Darth Tools package has not been installed. So just make sure that you can use the code that's already here, for example, and just uncomment this and run that to install Darth Tools.
Yeah, and you'll need to use dev tools for that.
Yeah, so basically it's best to install all the packages.
Yeah. Something we can also discuss at the end is how you guys would feel about learning about a specific package, like modeling package, hey, Karina? Because you've also been thinking about that. But the reason why we like to use this example is because it shows you the inner workings of how to calculate a Markov model, for example, in R. And it can sometimes be quite dangerous to just start off with a package, not really understanding how it may work. And this gives you a really good idea of how internally things work when you're calculating things or outcomes, etc. I referred to too many things there.
Yeah, I agree completely. And there's also a lot of commenting, explaining things, so it's relatively easy to learn. And they also have the whole tutorial published that you can follow to make sure you understand and that you're able to use this code to adapt it. I'm just looking at the chat. Vasily, you also have an error on NSAMP, but I just searched the code and there's only one place with NSAMP, but it's commented code. So I'm not sure what code did you run to get that. Make sure that you have this CSTM time independent.r open. And I see Josh answered the question about parallel processing. And then there's an error from Saim about the Darth Tools package. So make sure that you first install all these packages. So you can just uncomment them, run these installs, and recomment them so that you don't run it every time.
Yeah, so Saim, that error you got is because it hasn't installed. So as Karina said, at the top from lines in that script from lines 41 to 51, take away the hash sign. So uncomment them at the start of the line. So where it says install.packages from 41 to 51, just take away the hash at the start of every line and then let it install.
Vasily, you said you tried to run the PSA code, so I'm assuming from here you run this code. But did you also run the code before that? Because I think it should work if you first run the code before and then run this code.
Yeah, and you have to make sure that you've installed all those packages before doing that.
Yeah.
And the normal PSA should work, as Vasily has pointed out. Yeah. I wouldn't use the parallel stuff for now, just because it's not going to make much of a difference, just because it's not a very big model.
Yeah, and also, so the questions that I gave you are all basically up to all the uncommented code needs to be, or you can use that, except of course for installing libraries or packages in the beginning. Amrit is asking, how did I uncomment? So you can highlight code and then say Control-Shift-C, which uncomments it, and then again Control-Shift-C puts it back in comment, which is quite handy for chunks of code.
Okay.
Yeah, Bernardo, so yeah, no problem.
Hi, sorry. Were you you can finish your thought, Irina?
Yeah, no, I just wanted to, but I see Josh also answered. But Bernardo, it's kind of you can see it as a template. It is a basic model, so it's not only a template, but it can be used as a template to adjust, adding different health states, changing the transition probabilities, etc., to meet your needs. Thanks, Boucle.
Okay, cool. Thank you so much, Karina. We do appreciate it. So we are going to take a comfort break, and then we're going to have Hannibal present the next segment on interpreting cost effectiveness results. Cool.
Yes, like as Butler said, I'm Hannibal Msarora. I am an academic at Walter Sisulu University, and I'll be talking about how best we can interpret cost effectiveness analysis. So next slide. Okay, so to just provide a brief definition, this is something that you guys already know, but to just give it context and so that we can start from a similar position. Really, the essence of cost-effective analysis is to interrogate the costs that are poured into healthcare programs, drugs development, or whatever you can consider an aspect of it that is really going to incur any cost. How does it really relate to the health outcomes that you're going to get? So to do that, you need to have some sort of ratio that tells you whether or not you are going towards the right direction, and you want to make sure that you have got every dollar invested or every rand, rupee, or yuan invested in any program or in any drug development, you are going to get some positive return on investment. And the easiest way to do it is using the cost effectiveness analysis. So this is important for policymakers and decision makers, because really, like I said earlier on, you want to have a figure that tells you whether or not the change that you are effecting or you are intending to effect is going to be beneficial or not, or is going to be profitable or not, be it for the patients, for the economy, and for, in most cases, for the either insurance or pharmaceutical company who are developing the drug or whatever commodity intervention. So before we go too deep into that, actually it's an introductory workshop. We won't really go too deep, but I think before we start talking more about cost effectiveness analysis, I thought it was necessary for us to probably define the key concepts or terms that we need to keep in the back of our minds when we are talking about cost benefit analysis. Let's go to the next one. So yeah, I think the most important of one of them all are the QALYs. QALY just represents the quality adjusted life year, which is really the amount of life is added due to, well, quality of life, or how better your life becomes given a particular intervention. How is it better or worse? Then the DALY becomes almost the opposite of that. How much years time is lost due to the burden of disease. So what it essentially means is that if you are suffering from a condition, how much time is spent with you with that disability that is going to impact you living up to the expected life expectancy within the population in which you exist. And then we've got also another key term, which is the willingness to pay, which really is the bottom line that people are willing to pay, or that is considered acceptable to improve the quality or the DALY values. So it means how much is one or an institution willing to pay to increase the QALYs or to reduce the DALYs. Then dominance is just that strategy that is really more expensive and less effective. So this is the increase in cost with really marginal increase in the effect or the health outcome that you're measuring. So the stated dominancy, again, is the less efficiency, and that combines with many other factors. Okay, so when we are talking about cost effectiveness, there are a number of measures that we can use, another ratios that we can actually use to define cost effectiveness. Let's move on to the next one. Okay, so I think that the most important one that people often use is incremental cost effectiveness ratio, which really speaks to the amount of change in the cost as the ratio of relative to the change in the qualities or in the dalis. So it means that here, if you want to increase for every extra cost in the intervention, if you are using dalis for as your measure of health outcomes, then it means that with the increase in cost, you want that to be also be going up. If it's using qualis, then the opposite is true. As the qualis increases, you want and per unit cost, then the ICR should actually be the ICR should actually be coming down. Then all this can be represented using a cost effectiveness plane analysis. This is just a graphical representation of uncertainty and really the implications of the change in the cost versus the effect. So I think later on we'll talk about using the interpretation of the cost effectiveness plane. Then we have the cost effectiveness accountability curves, which again are also probabilistic, and their purpose really is to show uncertainty and which one is more likely, which options are more likely to be effective or cost effective than the others. So the idea again is to consider this one together with the willingness to pay value. How far higher are the new costs going for relative to the qualities and dalis versus the standard and the intervention. So usually with cost effectiveness, the point of departure is an already existing technology or an already existing method that's already been used. And with time, with the introduction of a newer one, you want to see if that newer one is actually going to be better or worse. And then there is the bottom line, the money that people are willing to pay for that particular change, for that particular service. So that's the willingness to pay value. And this is going to be coming up a lot as we talk about the cost effectiveness analysis. Okay. Then I think the last one is the what's the last value? Oh, yes, my phone is doing things here. Yes, the expected value per of perfect information. This is really, well, the cost of eliminating uncertainty, which really has more value in the future than in the present, actually. But again, in the same time, it speaks to the same thing, to directing us towards how to best improve or assess the effectiveness of the intervention or of the new drug, if that's the case. Now, I think let's go on to the next slide. Now, in R, there are a number of packages that you can use to determine the cost effectiveness of any program, any intervention. And this is a list that you can readily use, but the most commonly used ones are for me is the PCA and the SIM. These ones are easier to work with, and they usually also come with simulation sometimes, and they are rather comprehensive to work with. So for this workshop, I'm going to show you what I did using PCA to just assess the intervention of two, or the effect or the cost effectiveness of two interventions using comparing two different interventions, and at the same time with the standard, and also comparing those two interventions just one at a time with again with the standard. So this way you can actually see how best you can act. You can approach your cost effective analysis. In cases where you've got more than two and you want to do a simultaneous comparison, you can also do that. But in cases where you have just the one, you can also do them individually and compare results later on. But in cases where you want to do a simultaneous comparison, I've also showed them a way of doing that. Okay, let's move to the next slide. So initially I had real data that I worked with, but I had a challenge with my access to my other computer. So we're just gonna use this one for now. So this is a quick analysis using simulation really of two interventions that were compared against the standard, and we're using the BCA, the BCA, what do you call it, BCA package. And really, the first stage, as you'd see of this code that I'm showing here, is just simulating the data that you're going to use. And for consistency, I did use the set seed function. And yeah, so the first thing that we had to do was generate the cost, after which we generated the qualities, and we did the initial cost benefit analysis, which we use now for plotting the sorry, for the cost effectiveness plane plotting. So you notice that in the, let's go to the next slide. So I think the most important thing to note now is that the plane itself is going to be divided into 4 different quadrants. And for an intervention or a drug to be actually to be considered cost effective, introduction of a new drug to be considered cost effective, you want it to occupy the top right corner or the northeastern quadrant, because that shows that it has increased effect with minimal cost relative to the initial, to the standard drug. But as you can see in this case, it would seem like the effect is less, and because you can see that the dots that are on the graph are representing all the ISO values that have been calculated for this particular new drug, and yet the standard is in not much is falling in the top right corner. So because of that, you would consider it less effective. But if you look back at the simulation, Bushle, if you can go back to the previous slide. Yeah, so you notice that as we're generating the data, the mean of the standard drug, usually the first drug is going to be the standard. So the one that's in the first row, with the mean of $20,000, it's going to be the standard. Then the new drug is going to be the one that is having a mean of $25,000. And as such, you notice that although there is an increase in the qualities of 2.5 and the mean qualities the mean quality is 2.5 for the new drug, it is not it's higher than that for the old drug. However, when you do the cost effective analysis, that increment in by a few or two, the 1.3 or point whatever is going to be less than that. It's not going to be as effective as the initial the new drug. And as such, if you go to the next slide, you'll notice that the values are falling within the lower quadrant, meaning that it's not as effective as you would want it to be. And the red dots that you see there represents the mean ISA for this particular new drug. Okay. Let's move on to let's change the circumstance and move on to the next slide. Yes, that's it. Now, in this case, you notice that the cost of the new drug, which in this case is the improved drug, is less than that of the standard drug, and as such, it also has lower qualities. But when we go on to have a look at the plot, can you go on to the next slide? You will notice that now is the average, the mean ISA or effectiveness is much higher. And also it's the bulk of the values are occupying the upper top quadrant. This translates to a more cost-effective drug, and as such, you may want to, if you're a policymaker, to go with this one. Although there is an increment, the increments in cost is pretty much justified in this case, because as you can see, this intervention is more cost-effective, and this is actually better value for money compared to the previous one. And if you have noticed that the previous standard drug is actually costing more and is having less qualities compared to this one. Okay, let's move on to the next one. So in cases where you want to compare all the drugs at the same time, you can still go ahead and have all the interventions together in the same diagram, and you can do the whole comparison simultaneously. So in this case, I had both the improved and the new drugs compared with the standard. Let's go on to the next one. Yeah, so in this case, now you can see the difference between the two different interventions. You'll notice that the one is right up there in the top the right quadrant, and the other one is the bottom left, showing that these two are actually going in two different directions in terms of cost effectiveness. So if you see this stark difference, then decisions are usually easier to make. But often things are not as easy as this. This is simulated data, so the standard error and the standard deviation have been controlled, and because of that, you can see how neatly they fall into place. But in real life, this really won't be how things look, but basically, if you have this kind of separation, that's what you would want to look at, and this is what you'd want to use to make your decisions. It makes your life much easier, and then the stark difference can easily be explained. There isn't a lot of overlap, as you can see. That drug, the improved drug is much better than the new drug. So it would seem that there wasn't much of a change between modifying the new drug and the. Yeah, so my apologies, Ben. I made this too short. I'd had the other analysis, but then, well, like I keep apologizing, I couldn't access the initial file that I intended to present. But I think what I would want us to do, I have shared the script with Buhle. If you can make everybody have access to it, let's just play around with the figures, and then we do the other analysis. We can consider just increasing the qualities and dalis, and then you would see how the cost effectiveness is changed, and let's probably discuss that. So Bushle, over to you. If you can go out to the break rooms.
Okay, great. Thanks, Hannibal. So what I have done is I've shared the link to GitHub, where you can you guys can download Hannibal's script, and then so at the end of the breakout rooms, then Hannibal will I don't know if you want to ask, if you have questions or anything, maybe you can ask Hannibal then. Okay, I'll then go to the breakout rooms.
All right.
Hi everyone.
Hi.
Hi. So I think there were a couple of questions in the room that I was in with Karina. I don't know. Karina, were you able to open your script?
Yeah.
For this? Okay. Do you mind sharing your screen? Yeah, thank you.
Yeah. Yeah, so Hannibal, we were just wondering, when plotting the standard versus new isoplane and looking at the data here, I know that you're drawing random numbers, but to us, we expected a positive incremental effectiveness, because we would assume that this is standard and this is new. So then you have an increase, on average, you have an increase in incremental effectiveness. But when we run this code and plot this cost effectiveness plane, then we get negative incremental effectiveness and negative cost as well, incremental cost.
Oh, sorry, my mic was off.
No worries.
All right, yeah, I see what you're talking about. But in this case, the cost was higher for the new rather than the standard, isn't it? Yeah. So the second one is the cost of the new. So I think the effectiveness now needs to be lower. That's why the ISA values tend to be in the negative relative to the standard. I don't know if I'm.
But in this plot, the incremental cost is also negative. So we're plotting incremental costs and incremental effects that are negative. Unless I didn't run, but I'm quite sure I ran this code. Yeah, I did. So unless this is swapping around.
Yeah, the figures, eh?
Yeah. So if that this is new and this is standard.
But look, when we do it, okay, initially when you did both simultaneously, what did you get?
You mean here at the top?
Yes, right at the top. Because what we have here is just a split between the two. Because what you notice is that the effectiveness is going to be really showing in the improved one, because it's the one that probably by and large is having favorable responses. So in this case, I'm suspecting that, but I think I may have to relook at the code again and see what's happening.
Yeah.
Yeah, no,
yeah, because I think this doesn't seem to correspond to the inputs here.
Yeah, let me relook at it. Then I'll probably post the comments on the script on the top. Yeah.
Yeah, so I think the only thing that's happening is that for standard versus new, it's calculating the increment as standard minus new instead of new minus standard.
Yeah. Okay, I see what you mean. Okay, all right. You know what? I'll repeat this with a different package and see what I get. Probably then, and we can actually prove if it's doing that, because that will be a totally different thing altogether.
Yeah.
So let me get back to you. Otherwise, I'll be saying things that I'm not clear of myself.
No worries. Yeah. Okay. Thanks.
All righty. Are there any other questions? Maybe comments?
Okay. If there isn't, Hannibal, is there something that you want to maybe say in terms of wrapping up, or just as a follow-on regarding what you discussed with Karina? Will you post maybe a new script on GitHub, or just as a way forward?
Yes. So what I'm going to do is I'll run the script again, and I'll at least try to relook and see what's happening with that one. Karina is actually saying something right. It seems like the figures were swapped, so I need to look at the program, at the script rather, and change it. Then I'll repost it again. Actually, I'll share it with you when I'm done. Then you can post it again.
Great. Thanks, everyone, and enjoy your evening or day wherever you are. It was great being with you. Okay, bye.
Thank you, everybody. Bye.